So today I will not be telling you about a new post-processing code, happily, so I'm done with that. Instead, I will be telling you about some scientific results, projects that I've worked on using these different post-processing tools, and then try and give you an idea of what you can do and what kinds of cool scientific results you might come up with. So this is very similar to the talk that I sometimes give for colloquia on matching observational diagnostics with star formation simulations. But basically, the subtitle of this talk for this workshop is really fun things to do with post-processing tools. OK, so there's basically two ways to study star formation, right? So there's theory and pen and paper, try and derive things from first principles, or there's observation. You can go out and observe it. So the first reason is really why you're here. And this is the new face of theory, numerical simulations. Really, we don't do all that much pen and paper analysis anymore. And likewise, for observations, this is the new face of observing, these telescopes like ALMA. Now, traditionally, theorists and observers have often had difficulty talking to one another. And that is not because they do not like one another. It is simply because they're... That's true too. That might be true too, in some cases. This is being recorded, so I can't say too many hostile things about observers here. But really, it's one of different outputs. So theorists are talking about stellar masses, densities, velocities, these kind of fundamental physical quantities. And meanwhile, observers are talking about photons. And they often talk about mysterious things like antenna temperatures, velocity dispersions, and Janskis. And so there's a fundamental disconnect with some of the language that theory and observation have. So the way to fix this, of course, is that you want to take the numerical simulations and then post-process them, performing radiative transfer, and then getting photons out. And then observing them, so really moving them into the observational domain, and then you can compare apples to apples. So this allows you to compare and talk on the same level using the same units and the same quantities, which is an extremely useful thing to do. All right, so to illustrate this, I have a pop quiz for you. So the pop quiz is that one of these images is an observation, and one of these images is a simulation. So I want you to look at these two different images and try and figure out which is the simulation and which is the observation. All right, so who thinks that the one on the left is the observation? OK. Who thinks the one on the right is the observation? All right. I know some of you have done this before, so that might not, you've been in audiences before. But does anyone want to say why they chose one or the other? Does anyone want to, what features were you looking at? What particular things might you have recognized? Yes?
That I chose the left image to be the observation is that it has much more the detailed structure.
Mm-hmm. Yeah, there is a lot of detailed structure. Yeah. So there's an issue here. So how high resolution are the simulations? In some cases, they can be way more detailed than the observations. But in other cases, it might be the opposite. So, but I mean, it's a good thing to look for. Anything else? Sometimes people talk about noise, but they both, yeah. So I added noise to the simulation, but and it depends how well you think I can actually add noise to reproduce the observed noise. Anyway, OK, so I will tell you which it is. This one is actually the observation. And it's the Polaris flare, as observed by Herschel. And the reason that I started doing this and showing it in talks is because I saw this image, and I thought, hey, that looks a whole lot like my simulations. And then when you do an experiment like this, you do see there's a lot of features in common. There's filamentary structure, it looks very turbulent. But then when you look in detail, you find out that these two things are very different. One of these is a star-forming cloud. That is a simulation. It's about to form a lot of stars. This one is a high galactic latitude, very diffuse cloud. It is not, in fact, forming any stars. So on one hand, this might say something about the universality of turbulence, but on the other, it's a cautionary tale that says you really want to compare things in the same domain, in the same units, and then really try to do an apples-to-apples comparison, not just a qualitative visual comparison, which is sometimes done. Okay, so for these 3 different projects I'm going to talk about, first I'm going to talk about the underlying numerical simulations, and then I will talk about these particular projects so I don't have to revisit the numerical details each time. So I'm going to talk about a project using Hyperion, one using CATSA, and one using RedMC. So first, the underlying numerical simulations. So I used the Orion Adaptive Mesh Refinement code, which Chris actually talked about yesterday. And of course, we use this because we're interested in gravity, and AMR is very computationally efficient, allows us to zoom in on the regions of interest. These are the particular equations of hydrodynamics that Orion solves. You can see there's simply conservation of mass, momentum, and energy, and the Poisson equation for self-gravity. Now, to close this set up of equations, you can do one of 2 things. You can either solve an equation of state, so some isothermal component plus some adiabatic component, or as Roby talked about and as Jim Stone talked about also last week, you can solve the radiation diffusion equation. So for most of the simulations I'm going to talk about here, this is actually the equation that is being solved. Now the nice thing about this equation is you can actually add a source term in here, which can serve as a subgrid model for forming protostars. So in the subgrid model, you have protostars as sources. You can follow their accretion luminosity. You can follow the intrinsic luminosity and their stellar evolution, and then put this in a somewhat self-consistent way. Okay, so you have self-consistent radiative feedback within the domain and within the evolution of the cloud. All right. So I've made a movie of one of these simulations with YT. So this is going to be zooming in. This is a turbulent molecular cloud, and initially it's constant in time, but time will begin moving forward shortly. And we're zooming in on a particular collapsing region here, which is forming an individual protostar. C1 is also over there. And it's forming an accretion disk. So there's no MHD in the simulation, so we do get these somewhat largish accretion disks. So you can also look at the large-scale structure of the cloud as it's evolving over time. And here I combined 2 different images. The gray scale is showing you the very turbulent density component. You can see it's very filamentary. And the red and blue are picking out the forming sources. So this is showing you the radiation temperature here. And if you look closely, you can actually see some of these sources are binaries, like here. And you can see them as they are beginning to orbit around one another. This simulation is not particularly high resolution, that it can resolve close binaries, but nonetheless, you can see some of them forming from wider scale kind of filamentary fragmentation. Okay, so the simulations that I'm talking about today throughout this talk are all done with Orion AMR. They all have continuous large-scale turbulent driving. So we're driving on wave numbers of 1 to 2. So why we do that is because we think that most of the energy injections in this cloud is happening on the largest scales and cascading from those scales down to smaller scales. All the simulations have self-gravity, and we assume that the cloud is virialized, so the gravitational energy and kinetic energy are about equal. We also include sync particles, as has been talked about in several talks in detail. And one of the perks of these sync particles is, in addition to doing accretion and the typical things that these particles do, we also can attach a subgrid model, which can represent either protostellar evolution and or the launching of outflows. So in some cases, we can actually couple the launching of outflows with the instantaneous accretion of these sync particles and follow the feedback as this momentum is injected back into the cloud. So in this case, I'm also using, as I said, either an equation of state for one particular simulation, but mainly gray flux-limited diffusion. The resolutions are 256 cubed, either 4 to 7 AMR levels. So the goal of this work is to use these simulations to interpret observations and model reality, which is a great lofty goal, but very general, because you have to then say, what's the starting point? What are the particular diagnostics that you want to compare with? What are the most useful observable quantities? So one of the most popular observable quantities over the years has been the stellar initial mass function. Now, this is particularly handy because it is universal. So that might allow you to dispense with a lot of the detail of star formation. Okay? However, over the years, various people have looked at this with different codes, with different physics, with different initial conditions. And unless you're doing something pretty crazy, you can recover the IMF, at least this kind of distribution like this, in a not too difficult way. So there's maybe one thing that has an impact, which is whether you include radiative feedback or not. But aside from that, without trying too hard, you can get this back. So what we can conclude is this may not be the best observational diagnostic. So instead, there really are quite a number of things you can compare with. We have good measurements for protostellar kinematics and distribution, clustering, protostellar luminosities, outflow properties and evolution, molecular line profiles, core masses and shapes, and cloud properties. So over the past 5 years or so, I've worked on all of these different topics. And today, I'm mainly not going to talk about this one, and I'll focus on these three. So outflow properties, core masses, and shapes, and cloud properties. All right, so I'm going to start out by talking about a project using the Hyperion radiative transfer code that I talked about on Tuesday. And we're going to use that to try and investigate protostellar evolution. So the motivating question behind this work is how accurate are protostellar properties inferred from SEDs? Now, the reason why we ask this question is because the typical way of characterizing protostars is, for example, to do nice maps over a broad range of wavelengths, and then construct from all these different wavelengths an SED. And we do this because we may not have good resolution at particular wavelengths, so it's extremely unresolved. So the best you can do is make this kind of characteristic SED, which then can tell us about the protostellar stage. So then, the goal is to compare this with analytic type models to try and back out underlying properties that might go into this SED. And then if you do this and kind of get find a best fit model among all of these models, you can then try to infer a whole range of properties. So these include the age, the inclination of the source, the stellar mass, disk mass, envelope mass, disk radius, outflow opening angle, accretion rate, density profile, disk radius, envelope radius, and stellar radius. So there's a whole lot of evolutionary parameters and gas parameters that are really rolled into one particular 1D function. Now, observationally, unless you can directly resolve some of these things, which you usually can't, you really have no way of knowing how well you're doing and how well you should believe these parameters. So the goal of this project was to use numerical simulations, follow the same procedure, and then do the second step where you can go ahead and compare with the original source property in the simulation. So then you know how well observers might be able to recover these things. All right, so in this project we start with the simulations. We perform Hyperion synthetic observations of each of the sources. and then go ahead, compare these with a grid of models, the same grids that are used by observers for sources, find the best fit model, and then go ahead and compare with the original properties, which we know. So the simulations are, of course, using the Orion code, and in this case, we use a subgrid model for the outflows, which is based upon Matzner-McKee 2000. Okay, so we're trying to self-consistently model the gas morphology and the evolution around these sources. So one key thing that we had to do was going down to very low resolution, a few AU, when starting at a kind of cloud-sized scale, it becomes very computationally difficult and expensive. So instead what we did is we did one base calculation for a free fall time with relatively low resolution, and then we zoomed in on the individual sources. So we restarted the calculation several different times and evolved it forward down to AU scales. So this allowed us to get high resolution and also a broader range of scales and time over the cloud. So here's one of the outputs from the simulation. This is, again, a volume rendering in YT and showing you the gas velocity. So the outflows here stand out very nicely. The higher velocity gas, 10 kilometers per second, is in yellow. And then the kind of turbulent velocity you can see is around 1 kilometer per second or a bit less. So just a historical point, this is a very early volume rendering with YT. And at that time, it was really still under development. And you can see that because there are these grid artifacts, which are not actually part of the simulation. But it turns out to be a very difficult volume rendering problem to actually do volume rendering along axes. Okay? So the current YT is now, totally seamless and works very nicely. But this is, I think, one of the earlier examples of volume rendering that was done with it. Okay. So then, once we have the simulations, we post-process it. And for these different sources, we use 10 to the 7 photons. At the final time, there are about 21 protostars, those that were actually burning deuterium. We had 200 wavelengths between 0.01 and 500 microns, 20 different apertures. So we changed the aperture size to see the effect of variation of resolution. We had 5 different grid resolutions as we zoomed down from larger to smaller scales. And then we looked at all of the sources at 20 different viewing angles. So here's an example of what you get, comparing a resolution with 65 AU to 4 AU. And the convergence of the SEDs, you go from larger cells to smaller cells. What you can see is that for these range of cells, the long wavelengths are very well converged and are very insensitive to the resolution. The higher resolution is really being added in the inner regions, okay, around the disk area and close to the protostar. And you can see the SED is converging to this final value at the highest resolution. So if you look at the different wavelengths, you can see a lot of different structures pop out at different wavelengths. So at very long wavelengths, you can see kind of the disk a bit and some of the outflow cavities. As you go to shorter wavelengths, you begin to see the scattered light. You can even see a dust lane here. Here now the disk is not emitting at all. And as you get to very short wavelengths, you see a lot of scattered light. So on the left and right are 2 different protostellar phases. This one is entirely embedded and only has a very small outflow at this point. And this one is more evolved. So for comparison, this is an actual observation of an outflow. And you can see that a lot of the features that you see here are also seen in the simulation. So with all the different protostars in the simulation, we have a whole zoo of SEDs going from very early phases to later phases. I think there's one here. So you have a range where you just see the envelope and where you begin to see some of the scattered light and emission at shorter wavelengths. So one interesting thing to compare is the bolometric luminosity inferred from the source, from the SED, compared to the true luminosity of the protostar. So the actual luminosity of the simulation is in red, And the blue is showing you the range depending upon the particular viewing angle that you're looking at. So if you're looking through the disk, it might look much more extincted, so you infer a lower luminosity. But if you're looking down through the outflow cavity, you might see more of that emission, and so you infer a higher luminosity. In some cases, within the particular aperture that we were looking, there's a secondary. So you can see that one of these particular ones is dominant, but there is a secondary source that's contributing luminosity. And this might, in fact, make the SED or the interpretation of properties more difficult. So one fundamental problem observers have is when looking at these sources, trying to determine how old the source actually is. Okay? So trying to assign a physical stage of evolution. So as Neil Evans talked about, this is actually quite hard. And it varies depending upon what viewing angle you look at the source. So instead, what observers do is they've defined something called the bolometric temperature, so a characteristic temperature of the SED, and use that to make up a class system. So here, you can really see what happens to a given source if you look at it at different viewing angles. So at this particular output time, all of these sources basically should be in this lower panel. Okay, these are physically very, very young sources. But what happens is, if you start looking down different directions, particularly close along the outflow cavity, then you begin to infer much older ages for these sources. So here the actual age is in blue, or the actual, I should say the median age is in blue, and the red gives you the dispersion of inferred ages depending upon the direction you're looking at. So what you can see is it's really easy on an individual source basis to completely get the age wrong. Okay? And this is a problem because observers use these statistics to try and infer ages and lifetimes for these classes, which would then translate into physical ages. But it's really, the way of doing this really has a lot of error in it. All right. So in order to infer direct protostellar properties for individual stars, what we did was we compared with a model library from Tom Robitaille of 200,000 model sources. And this has been used quite a lot by observers over the last 5 years. It's very easy to use. There's an online app for it. You can feed in your observed properties, and it will try and match it against this library and then tell you the best fit models. So it's a really nice thing that has been used quite a lot. So we did the same thing that observers using this application would do, which is looked at the sources of the observations, looked at the sources in the simulations at particular observational wave bands. And then here, we fitted against these models and got a best fit in black, and the good fits in gray are also shown. Okay, so basically the same procedure at the same observational wavelengths that observers use. So here's what we find for a variety of different parameters. So this is the ratio of the model value that was inferred to the actual value of the simulation. So 1 is what you want. You want the model and the simulation and the inferred value to be the same. So the red shows you, the crosses show you the best fit model, and then the range is giving you the range of parameters for the good fits. So what you see is that there are a number of cases that are within about a factor of 2, which is actually pretty good. But as you go along here, you see there's also a number of sources that are wildly misfit. And part of that is, as we go along here, these early ones are very isolated. And as we move forward in time, some of these sources are becoming more clustered. And so you do have contamination. They're near another source. And the morphology of the simulation is becoming more complex. So this is definitely creating problems with inferring the intrinsic mass of the protostars. Then you can look at stellar radii. I mean, this one is really a wild card because it really depends on the protostellar evolution model that we use in the simulation. It depends upon the one that Tom used. And both of those might be completely unlike the actual way that protostars evolve. So here, even getting within a factor of 2 is probably pretty good here. We also compared the log of the accretion rate. That's actually looking a bit better. It's mostly clustering around 1, and the best fit models tend to be closer to the line than the good fit models in most cases. So that's somewhat optimistic. And the reason that that fits so well is at early times, really the luminosity, which is the main integrated thing that you get out of the SED, is determined by the accretion luminosity. So if you know the net luminosity, and you try and infer the accretion from that, that's probably not too bad in terms of the correspondence. So to give you some idea of how this happens, here's the total distribution of models as a function of accretion rate. So there are 200,000 of them. For a given luminosity, here's the range of good fit models, and here's the actual accretion rate. So it's not doing too badly, but there is a spread of almost 2 orders of magnitude there. Or yeah, almost 4 orders of magnitude here. But then this is really being constrained by luminosity. So if you just fiddle with the inferred luminosity by 10%, all of a sudden you begin getting more and more accretion histories. So this is really sensitive to that integrated luminosity of the observations and of the simulation. Finally, we have the inclination, which is within a factor of 2, usually not too bad. But really, plus or minus 20 or 30 degrees is probably not particularly sensitive to the inclination. That's probably as good as we can do anyway. Finally, we looked at the recovered envelope mass. So if you look at long wavelengths and then convert that into a mass, you would say, okay, that's the total envelope mass associated with this protostar. But what we uncover here is really something fundamental about dust, okay? So inferring the mass from the emission, you need to know what the dust properties are. So here, Orion uses a model which has icy dust grains, okay? And Tom's code uses a model with different size grains that are not icy. So already here we get a factor of 7 difference, okay? And then if you're looking at a particular region, you probably want the icy dust grain model, but maybe there's some completely different model. So even between these 2 cases, we have huge amounts of uncertainty. If we're looking at short wavelengths, now we have inclination and temperature effects, which are pretty annoying. If we stick to slightly longer wavelengths, then we get a much closer scatter around the expected value, but it's still not particularly good. So basically, in total, it's somewhat bleak. I mean, within factors of 2 is pretty good for some of these quantities, but many of them are completely unreliable. All right. So any questions about that before I move on? Okay. All right, so now I'm going to switch gears and talk about interferometric observations of dust continuum. So now switching to using CASA to post-process simulations. So the motivation behind this question is, what is the initial stellar multiplicity? Now, a lot has been made of the stellar initial mass function, but you can also try and ask, what is the multiplicity of protostars? How does that evolve as a function of time? And what we see in the field may not be the initial stellar multiplicity, because things can change dynamically. So we really don't know at early stages. Observationally, the problem is difficult because things are deeply embedded. You may not have the resolution to resolve very close binaries. And even if you do, it may be difficult to tell if those 2 protostars are bound and if they will remain bound over time. Okay? But we can try and get at this problem with simulations. So there are 2 paradigms, or 2 main paradigms, to produce multiple systems at early times. The first is turbulent fragmentation. So the idea behind that is that cores are not spheres. They have some structure. They have some internal turbulence. And you might have a particular core that might look like a particular gene's mass, but within it, the substructure might independently collapse and create a multiple star system. So an example in the simulation might be something like this. We have a kind of messy filamentary structure that collapses into 3 objects. And I think in this case, the final result is one of these is not bound, but then 2 of them do actually converge and become bound. The second possibility is disk fragmentation. So in the other case, the fragments are initially much wider separated, but you can get very close fragments if you have gravitational instability within a disk. So here's an example of a accreting protostar with one of these very wide disks. What you can see is that this disk is actually quite unstable, and you can see these large spiral modes developing, and at some resolutions and for some simulations, you actually see fragmentation within these spiral arms, which then may go on to form binaries. And I'm sure Caitlin Crater, maybe 2 weeks ago, showed you some nice simulations showing binary formation from fragmentation. Okay. So then the question is, what is the correct answer? What is the correct mechanism as a function of mass? Now we see that most high mass stars are in binaries, but most low mass stars are single. So in these simulations I did, including radiative feedback, what we found is that disk fragmentation was almost entirely suppressed because you had heating from these forming stars as accretion luminosity, but turbulent fragmentation still happened and could in some cases create close binary systems. So the idea is that, okay, if these are happening in the simulations, we can actually go out and look for these observationally and try and predict at the earliest times what the multiplicity might be and how it might arise. So this problem was inspired because somebody did go out and look for these types of structure in cores. Scott Schnee looked at 11 starless cores with KARMA, and he also had lower resolution images in Bolocam and Scuba, so that's in red. So what he found is that lower resolution, some of these two images look like they have structure. They're elongated. They look like they might have some fragmentation or something going on. But then when he looked at high resolution with interferometry, he basically found no structure. So there was a single peak in each of these cases, or in many cases, no detection at all. So he concluded there was an observed lack of substructure in starless cores. So this is a problem for turbulent fragmentation theory. So if there's no substructure, if there's no turbulent structure, then there might be no fragments. And if there's no fragments, then you can't really form wide binaries in this mechanism. So the question is, did he not see any structure in these cores because there is no fragmentation? Or is it because these particular cases will never go on to form stars or even binaries? Or is it just because this turbulent fragmentation picture is really hard to see at early times, even with KARMA or even possibly with ALMA? So in order to investigate this, I used the CASA software package to basically mimic KARMA and ALMA observations, including noise and beam resolution, to try and really reproduce his observations and make predictions. So we start with this AMR simulation, including radiative feedback. I computed the dust emission at longer wavelengths, ran that through CASA, and then compared directly with his observations. So here's an example of 3 different cases in the simulation which are in the process of fragmenting and forming a binary, or at least forming a wide stellar pair at early times. So you can see here there's a lot of structure. But now, when you go ahead and observe these with KARMA using the same resolution that he did, it's completely wiped out. So maybe there's a very weak detection, which is consistent with many of his non-detections, but basically you see nothing. So the question is then, what would ALMA see in the same circumstance? So first we tried early science. And what we find is very disappointing. So early science is 16 antennas, and what you see is one single detection in each of these cases. It's a very strong detection, but you see virtually no structure. And this is because the larger scale structure is basically being resolved out. But then you can go ahead and look in full science configuration, so 50 antennas, and then you can actually begin to recover some of the structure. Now you clearly see too strong detection. You see structure within these cores, and you even begin to see some of the filamentary structure that's appearing in this one. So this is actually really good. But when I looked at this, after doing this, I thought, ALMA is, it's taking a lot of work, it's very expensive. Is this really the best that we can do with ALMA? It's somewhat disappointing because a lot of the structure is still missing. So it turns out there's a way that you can observationally try and recover that. And that's with the ACA, this Atacama compact array. So the idea behind this is to add additional antennas which are smaller. So that means they can actually be closer together and resolve larger spatial scales than you would with the regular 12-meter antennas. So you can do the observations here simultaneously and then combine the data to give you a much broader range of spatial scales. Okay, so for comparison, here's the full science, and here's full science plus compact. So now we've recovered almost all of the structure, and in cases where these are there's no current protostar here, these are about to form stars, we can see almost all of the structure within these cores. So this is making a very strong prediction that early interferometry, you couldn't see this, but ALMA can. So this means that if ALMA goes out and looks at these cores and doesn't see anything, then there's a problem. So this is really good to make predictions like this, because this will really tell us very fundamentally about the process of binary formation. And hopefully, we will resolve this in the next few years. All right, so now I'm going to move on to observations of molecular gas. So this is now a project using RADMC 3D. So now we will go out to much larger scales. You remember that Paul Clark actually showed this same observation last week. This is the Perseus cloud observed in 12CO. And what you can see is that there's a huge amount of structure here. This is a data cube in position velocity. And you can see there's a number of different features. You can see very complicated loops here. You can see substructure. And over the cloud scale, there's just a huge amount of interesting structure. But the question is, how much of this is real? How much of this corresponds directly to features in three-dimensional density? Okay? Now, observationally, that is extremely hard to answer. But with simulations, we can try and get at that problem. Okay. So the problem is there are a couple things that can happen on the way from going from three-dimensional density to position velocity, going from density into the spectral line space of 12CO. Okay, one thing that can happen to mess up the correlation is superposition. So imagine if you have three different clumps here. These clumps along line of sight, two of them have the same velocity or very similar velocities. One of them has a different velocity. Then along the line of sight, when you do the translation from position along the line of sight to velocity, these two will get mapped to the same velocity space. So now you started with three different structures and you've ended up with two. The second thing that can happen is you can create artificial structures. So suppose you have a blob where spatially it's coherent, but with inside there are two different velocity components. Then when you map this from position space to velocity space, you might break up the clump and it would look like two features instead of one. Okay? So both of these could create problems. So the way that we looked at this problem was by characterizing the structure within clouds using dendrograms. So dendrograms are basically hierarchical structure trees. And the idea is that we can basically look at the hierarchy of structure. We can find structures within structures. And so we're not just looking at the top level of structures like you might do with clump find, but we can look at embedded structures and see how they relate to one another. So this type of algorithm works with both intensity and with density. It works on 2D or 3D. And so we can run this on both the observations and the simulations in the same way. Yeah, so the terminology for these things up here are leaves, and then you might call this the trunk. Okay, so after running this dendrogram on a particular data cube, you then have to define parameters to say how well you're recovering structure and how similar are these structures. So I'm going to do a very simple example here. So suppose in three-dimensional space in density, we see there are three different structures where one is inside another one. Then if we map these into position velocity, we might get something that looks like this. So now two of these are overlapping, and then we have one here that still remains inside the larger structure. Okay, so then how do we match them? And how do we tell how well we're doing with the matching? All right, so consider this identified structure O1. So O1 looks a little bit like R1, but also looks a little bit like R2. And if you compare on a cell-by-cell basis, which you can do in the simulations, then you can see, well, the overlap is slightly better with R2. So then we say it matches R2 and has a similarity, a goodness of match of 0.5. Likewise for O2, if this is O2, which we've identified in position velocity, we can then compare it to these structures. And we see it compares completely dissimilarly with R1. It compares a little bit with this R2, but it almost entirely matches this original R3. So then this, we would say the match is R3, and has a very high similarity, okay, of 0.9. All right. So in order to quantify this, we use one of these Orion simulations of a turbulent cloud, where we tried to match the average bulk parameters of Perseus. So we tried to match the average column density and the average velocity dispersion. So then we ran RADMC3D on it to generate 12 and 13 CO data cubes. And then you can compare also what you get for the emission and for the actual distribution of RMS velocities. Now what you see here is that it's a very tricky problem. And we spent quite a number of months being somewhat annoyed by trying to do this matching and trying to come up with the correct parameters that we should match. But even so, with a few iterations, we still have this offset here between the intensities of the data, which are in black, and the intensities of the simulation. So clearly, the more parameters we have to match, the harder it is to match these distributions. So this is something I think might require some future work. But nonetheless, with this simulation, we can go ahead and do this experiment and see how well we can recover the structure. So here's what it looks like. Here's the mean brightness as a function of the area, or the effective size. And here's in 12 CO, 12 CO 3 to 2, 13 CO 1 to 0, and this is Perseus. So what's being shown is for each of these different clumps that have been identified in the data cube, we plot the match quality. So how well it corresponds to a feature in the 3D density space. So blue is good, red is bad. So what you can see is the situation is pretty terrible. For 12 CO, there's really poor match quality. You can see that up here if you just look at a slice through the data cube. Most of it is kind of pink here. And then as you go to a higher transition, it gets a little bit better, but not very much. And really, the situation only begins to look good when you look at 13 CO. And the reason is because 12 CO is really a poor tracer of detailed cloud structure. So here, this 12 CO is becoming optically thick, and you're losing emission because it's most of the cloud is emitting in the CO. You get a lot of blending of features. And some of this is separated out when you go to a higher density tracer of 13 CO, which has a slightly lower filling factor. So the 13 CO actually looks pretty good in terms of the distribution of Perseus 13 CO data. So maybe we can actually believe some of those structures that are being found. Now, you can verify what's going on with the CO by turning off the opacity. So basically treating the CO emission as if the entire box is optically thin. So then the lines never get saturated. And in that case, you see much more spread, okay? So if you have some way of creating differentiation in the CO, if you're not becoming saturated, if things aren't quite so confused, you do a better job. So we can also compare the case where we have chemistry. So chemistry helps the CO in a couple of ways. So it helps because, well, you can dissociate the CO. So then there's less CO to create the blending. And the chemistry can also, if you have temperature variations within the cloud, which you do if you have some external heating, you can induce a temperature range of maybe 10 to 100 Kelvin. So in that case, you're actually moving the emission around a bit. So in that case, the match quality is a bit better. It actually creates problems in terms of structure properties, which I don't really have time to talk about, but you can ask me if you're interested. All right, so now if we go back to the 13CO, we can then ask, all right, what are the properties of these objects, and how well do these match to real objects? So again, the color scale is showing you the match quality where red is bad and blue is good. So then when we do these distributions, you can then take out the bad matches and see if that affects the underlying trends that we observe. So here's velocity dispersion, the mass of the cores, and alpha, the virial parameter. And you can see that these, for example, this matches fairly well with the line with size relation. And the objects that are creating the most scatter are actually the ones that are bad, that have a very poor correspondence. Okay? So that actually does help us. And we can see that that might be one way of reducing scatter in some of these observed relations. All right. So are there any questions about that? All right. Final. So I guess moving on to the summary. So basically what we've seen is that these synthetic observations are a powerful and necessary tool for studying star formation. We can pull out a lot of different properties using them. In the first part of the talk, we saw that the SEDs and these inferred properties were very sensitive to the viewing angle that you looked at the source, which means that it's very difficult to tell the properties of an individual source, okay? Sources might then span two classes, even if they're extremely young, as only less than 30,000 years old. And ages can be overestimated in maybe 5 to 10% of the individual sources. So caution is necessary when extrapolating these properties, and you have to be careful about which ones that you infer from the models that you believe. In summary 2, we found that observing turbulent fragmentation is hard, and that was true even with ALMA. So KARMA was horrible, but with ALMA, it was difficult unless we were able to really use the full science array plus the compact array together. Then it was possible to recover all the structure. So hopefully in the next few years, we'll begin to see how much of this structure appears within cores. And summary 3, we find that cloud structure identified in 12CO may not in fact reflect real cloud structure. Some of it may be blending or artifacts, so you have to be a little bit cautious with some of those properties. The problem is probably worse in regions with high optical depth and strong clustering. So maybe the CO will be much better in more diffuse regions, for example, like Taurus. And then finally, UV heating and chemistry helps a bit by lowering the abundance and hence the optical depth, but it actually may create artificial structure due to some temperature and abundance variations. So that's adding extra degrees of freedom into the problem. And finally, the prospects for 13CO and higher density tracers are much better. So in terms of trying to infer properties, 12CO might help you understand the bulk structure, but 13CO is really necessary to get at the structures of smaller features and within cores. All right, any questions? Yes.
So I was wondering if you look at other chemical tracers in addition to isotopologic CO to match, make sure that the structures you're seeing are actually real, if that's not.
Yeah, so one good thing to do might be to look at N2H plus or ammonia. So these are higher density tracers. And we would expect the filling factor of that to be smaller because it's tracing just the denser gas. But we haven't looked at that. Yeah, it's worth looking into. Any other questions? Yes, Chris.
Stella, on the 12CO, basically, as you point out, because it's optically thick, I would think that it would be better at just getting the very large scale structure. So did you try seeing how good a job it does on the large scale?
Okay, so in a way we did do that. So let's, okay. So since this is the dendrogram, it's hierarchical. So the larger scales are basically this. So as we're going down and including more and more of the cloud, this is the entire cloud. So you can see as you go from smaller scales, which is the denser stuff, to the larger scales, you do actually improve going from red to white. But it's still not that great. All right. If there are no other questions, I guess we'll have a coffee break.
Coffee break it is.